Hello, madam. Hello, sir. This is Darnapu Ganesh. Hall ticket number 21955 A0302. Mechanical in third year, fifth semester, mechanical engineering, Iare college. Now I'm going to present my TikTok concept video, TikTok video topic on machining of nickel-based alloys using different cementite carbide tools. Introduction: increasing the productivity and the quality of the machined parts. Sorry. Increasing the productivity and the quality of machined parts are the main challenges of manufacturing. Main challenges of manufacturing industry. Modern cutting tools allows cutting at high speeds, thus increasing the volume of the chips. But removed per unit time and the objective requires better management of the machining system. Corresponding to the cutting tool machine tool workpiece combination go towards more rapid metal removal rate. Exploring higher cutting speed depends to the greater extent on the cutting tool machine. This slide is telling that quality of a machine parts day by day, production rate is increasing and the quality of the product also increasing, and also modern cutting tools are high speeds and thus increasing in their whenever the machining is going on, the metal removal, the volume of metal chips removal rate is increased, in the sense the volume of chips removed when the cutting tool is speeding at movement also increased towards more rapid metal removal. Whenever there is a increasing in the cutting speed, automatically the metal removal rate also increases rapidly, and cutting action greater extent on the cutting tool materials. Whenever the cutting speed is greater, then cutting tool material also automatically it is also greater. General information on operating parameters employed when turning nickel based alloys available in both academic and industrial literature. CT, tool constant, tool life constant, depth of cut, feed rate, surface roughness, tool life, cutting speed. Tool life is constant. If we consider 10 tools, 10 tools tool life is constant. The tool life is not going to vary, or it is not going to change. The tool life is must and should be constant. Depth of cut. The depth of cut, we don't know how. Whenever the speed is the tool is rotating at high speed, the depth of cut is defined as how long the material how long the material is how depth the material is going to cut, and the how the amount of material is going to remove, that is known as depth of cut. How long the material going to cut. Feed rate, how much the amount of speed is giving to the tool. Surface roughness, tool life, cutting speed. From the beginning development of an architect development, adequate prediction theory process was a major concern for all researchers. In the relation to machining operation with defined cutting edges, the workpiece surface integrated aspects turning inconal with coated carbide tools. It is a material and mm, here for the cutting tools are made up of cementide carbide tools. Cementide carbide tools. And also these cementide carbide tools are coated with inconal 718 material. And due to their high temperature strength and high corrosion resistance, nickel alloys are used for engines. For commercial and military aircraft and airspaces. It is considered by machinists one of the most challenging areas. The nickel and nickel alloys are used for in engines for IC engines or normal engines and also commercial, and it is also majorly in military area and aircraft. Why the nickel is going to be used in aircraft or space engines? Because of unique character, like it has less weight. The nickel has less weight. It can able to withstand high weight or high load. So these few are the unique characteristics of a nickel alloy. That is the reason aircraft and space engines are using nickel alloys. This is due to complex of material properties, namely to thermal conductivity leading to increased temperature. At the tool point rate phase, the work hardening tendency during machining, the high thermal effective to material resulting in welding adhesion of workpiece material to cutting edge, presence of hard abrasive particles, example carbides and oxides, resulting in tool wear. And also the main character unique character of carbide tool is it can easily withstand the wear and tear resistance. I repeat, the cemented carbide tool has a unique characteristic, that is it can easily the cemented carbide tool easily and able to withstand the wear and tear resistance. That is the reason in every cutting tool almost the cemented carbide tools are using. And also high speed carbon steels or a HSS high speed steels are, these three are the mostly used tools. Among these three, cemented carbide tools are used more because it consists of carbides and oxides. So that is the reason it can easily withstand the tear and wear and tear resistance. In generation, due to cutting operation is the systematic plastic deformation. Tool and workpiece and between the tool and chip. Metallurgical challenges that have improved superalloys, coming the metal stronger, tougher, or more resistant to the oxidation or machine. For the nickel-based superalloys, high temperature characteristics translate directly to machining challenges. The combination of high cutting force and the high temperature when machining these material leads to edge breakdown of the through the chipping deformation. In addition to, for the majority of the metalwork hardening takes place rapidly. A hardening surface is created during machining can be result in depth of cut line, notching of the tool, and many also compromise the fatigue strength and geometric. From this side, nickel based alloys are known as super alloys, and it have high temperature characteristic. It have high temperature characteristic temperatures, and also it leads to edge breakdown because of chipping or a deformation. And also it the nickel has work hardening takes place rapidly. Hardening means, and also whenever the hardening surfaces are machining, definitely the depth of cut line is notching of the tool, and also fatigue strength is going to be decrease of the tool. Many nickel alloys are age hardened, enable machining that the hardness of the alloys increases dramatically upon heat treatment. As second phase, particles from the alloys become stronger and more abrasive, difficulty to measure. The geometry of the tool plays a big part in controlling heat. The geometry of a cutting tool must allow for chip removal in order to take the heat out with the chip. The tool geometry should allow for smoother cutting and less vibration, chip evacuation. In addition to higher RPM, speed rotate, depth of particle required maintaining flow, chip and heat. In this slide, whenever the heat treatment is given to the alloys, the hardness of the alloys may be increased. This leads to the stronger and more abrasive, and this leads to it is difficulty to machine. I repeat, whenever the nickel and alloys are increased, given heat treatment to the nickel and its alloys increases hardness, and whenever because of this increasing hardness, the alloy becomes more stronger and more abrasive. Then it leads in difficult to machine the alloys and nickel and its alloys. This study intends to investigate the effect of tool holder geometry on cutting performance in terms of tool life and tool wear when the machining of nickel alloys. The higher surface roughness values can be explained by the high ductile nature of a nickel alloys, which increases the tendency of form a large unstable built-up edge. Presence of large unstable built-up edge causes poor surface finish. It's seen that cutting speed had a significant influence on the surface roughness produced. This line explaining that highly ductile in nature of nickel alloys, which increases unstable and large. So automatically BU, I repeat BU, that means built up edge will be formed when the nickel alloys have high ductile in nature. So build up edge can be formed. Build up edge. BU stands for build up edge. And also the presence of whenever the large unstable build up edge is formed, it leads to poor surface finish. I repeat, whenever the build up edge is formed on the surface on the large and unstable, then automatically the surface finish is going to be very poor. It's in that, and also cutting speed also influence the surface roughness produced. I repeat, surface cutting speed also importantly dependent on the surface roughness produced. Tool wear. The decreasing in the surface roughness which increase the cutting speed can easily explain by the different waves operation in the cutting inserts that were predominantly occurred in two regions during the tests at the depth of the cut line and the nose of the radius cutting, where at the depth of cut does not have any influence on the machined surface roughness. This slide itself explaining that decreasing whenever the surface roughness decreases, automatically the cutting speed of the tool is also going to be increased, and also the depth of cut line and depth of the cut line and radius of cut line also going to be decreased. However, the wear at the nose radius of cutting edge directly influences machined surface roughness, since the nose edge is in direct contact with newly machined surfaces in the form of noise radius wear for speed with another speed increases. However, the further increase in the cutting speed increases the extent of tool wear. Furthermore, cutting during chip formation, the small fragment breaks off chip and become lodged in the contact area between the workpiece and tool. The given high forces in the area, the particles can become pressure welded to the cutting edge. Particles can break down the cutting edges, pulling carbide with some rapid tool wear. They can pick up easily large pieces of the tool surface to clank, flank, and wear edge chipping. Whenever the cutting speed increases, that the extent of tool wear also increases. Nothing, simply is saying that whenever the cutting speed increases, then the tool wear of the wear of a cutting tool also going to be increased. Then the fragments break off, and also chips from the fragments also break off, and these particles get logged, and these dust particle or fragment particles contact with the workpiece, and also the between this contact between workpiece and the tool, and also rapid tool wear also going to be happen. You can see that this image, chipping wear and nose radius of wear. This area is a chipping wear area. This area. This is a gauge fracture. Tool life. Tool life is often most important practical consideration in selecting cutting tools and cutting conditions. Tool wear and fracture rates are directly influenced on tool costs and part quality. And understanding that tool life requires an understanding of the ways in which tool fails. Tool life is implemented essential to reduce cost of production as much as possible. Cutting tool have a limited life due to inevitable wear and failure. Advances must found that increase tool life the crucial parameters of the cutting process. The cutting tool fails either by gradually and progressive wear of its edges or to reduce chipping or plastic deformation. How the tool life is going to be increased? The tool life going to be increased. These few points you need to keep in these few points in your mind. That first point is the material of the workpiece should be or the hardness of the workpiece should be less than the cutting tool. And second point, the speed of the cutting tool should be medium, and also the depth of cut also should be medium, and also the chip removal rate is also medium. These are the few points to increase the tool life. And also, whenever the heat interaction happen, in order to increase the tool life, we need to use the coolants in order to increase the tool life. Progressive wearing of its edges are due to chipping or a plastic deformation. Usually, the tool life defined as the threshold value of cutting weight. Clearly, any development in tool or work material increases, tool life will be beneficially. Continued efforts are made to find ways of using cutting tool to the greatest possible extent before they fail. The most widely used tool life equations is Taylor tool life equation, which relates to the tool life t minutes to the cutting speed through the empirical constant. It is very simple that in order to increase the tool life, threshold value of a cutting wheel should be defined. And also tool and work material also increase the tool. Work material, actually in previous slide already discussed that workpiece material and tool also going to increase the tool life, already discussed there. When the cutting speed increases, the tool life also decreases consequently. In first slide only we discussed the speed of cutting is inversely proportional to tool life. That means whenever the cutting speed is increases, the automatically gradually the tool life is going to decrease. In order to increase the tool life, it is better to go with medium or low speed of a cutting tool. It is the best part. As chipping wear, grass fracture, the cutting speeds in spite of chipping, but tool uses unstable and surface roughness values was the lowest for the same cutting length. But when the increasing cutting speed, the surface roughness also increased dramatically with total ending the tool life. When the cutting speed increases, the surface roughness also increase, and then automatically the life of tool is also going to be decreased. Finally, the conclusion of the nickel-based alloys using the cementite carbide tools. Turning tests were performed on a nickel-based alloys using two different cementite carbide cutting tools. The influence of a cutting speed tool, insert and workpiece material were investigated on the machined surface roughness. Based on the result obtained, the following conclusion: cutting speed was found to have a significant effect on the machined surface roughness values. And we conclude that if the surface roughness of a material will have more, automatically that the carbide tool unable to, or it can't withstand the that much of the surface roughness when the machining is operation is going on. And also effect on the machine surface roughness values. And also whenever the machining the workpiece or work material should have less surface roughness values. Higher roughness values as a result of gross fracture, cutting edge diameter. If the workpiece has higher surface roughness value, automatically results in the tool maybe get fractured or formed cutting edges when the tool has at higher speed, and also when the tool is going to be at when the workpiece has higher surface roughness. Thank you.